So in the morning, I gave you this quantum formalism based on state vectors, and I told you, all we need to do is to prepare some initial state in 0 or 1, and then apply unitary and then measure. You might be wondering, how is this possibly the general description for quantum physics? There are lots of other operations you might want to do, such as prepare a few qubits and just discard some of them, right? This is a legit operation. So how do we describe this formally in a mathematical framework? And that's what we are going to do next. So I'll give you the second system for describing quantum information based on density matrices. So let's directly jump into it. Okay, so let's come back to a single qubit, right? So it's just a vector in the 2D complex space. And then this new description I'm going to tell you will write this single qubit state as a matrix. And in fact, we're going to take the outer product of this vector. Okay, so this is a very compact notation. You have a column vector, and then you multiply with the row vector of the same thing. So this gives us a 2x2 matrix, and we call this a density matrix. And let's just quickly look at how this works out. So take an arbitrary single qubit state and write it as a column vector. And then let's do the row vector. The broad side is going to be alpha beta, but don't forget the complex conjugate. And then this outer product will become, well, as you would expect, we have alpha squared here, and then alpha bar beta, and beta squared. Okay? So as a special example, suppose alpha beta equals 1 over square root 2. This is the quantum coin. Then this outer product will look like half, 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 half. Okay, so we're going to call this a density matrix. Okay, now another example, real quick. Suppose I start with psi, all right? And then I do a measurement under the computational basis. According to the rule of measurement, we're going to see 0 with probability half, and 1. The resulting, the posterior state will be 0 with probability half, and Kt1 with probability half as well. So how do we describe this posterior state in a compact way? Well, this density matrix formalism will be very convenient here, right? So in this 0 case, we can write down the corresponding density matrix, which is K0 bar 0. And for 1, we can also write it down as Kt1 bar 1. Now, how do we combine this? Well, we know it's just going to be a probability mixture, meaning with half probability, you get this matrix, density matrix. With half probability, you get the other one. So just take this. This will be the density to describe the posterior state of this measurement. And in matrix form, it will be diagonal with half on the diagonals. Okay? And let me just point out, this process, if you just care about the resulting state, this is the same as flip a coin, a classical fair coin, and then prepare a quantum state accordingly. For example, if it's heads, we prepare K0. And if the classical coin lands on tails, we prepare Kt1. Then the resulting state of this process, it will give us the same density matrix. So this is just for a single qubit. Now moving on to multiple qubits, and also more generally, when we have multiple possible states. So suppose we have a probability distribution P1 to Pk. So they sum up to 1. And then there's correspondingly a bunch of possible quantum states, psi 1 to psi k. Okay. Now, suppose we're going to first pick an index j according to this classical distribution. And then prepare a state psi sub j. Then how do we describe this resulting quantum system? Well, in the old formalism, we can just write this as an ensemble, or just a set of quantum states, pj, psi j, meaning the system is in state psi j with probability pj. But then in the density matrix formalism, you can write it down compactly, just following the same idea as before. We know for each j, we can write down a density like this. And since each one will be chosen with probability pj, we take this weighted average, and this whole thing will be the density matrix describing this system. And then usually we're going to write using a lowercase Greek letter, like rho, sigma, pi, to denote a density matrix. Okay, so again, this is just a weighted average of a bunch of possible quantum states that we are familiar with. Okay. Now, let's go back to these first two examples. As we can see, there is a difference. In the first one, there's just one single component. It's coming from the state psi. In example 2, it actually can contribute by 2 possible components. And this is a qualitative difference. So if we can write it as a single component, the outer product of a single component, then we call this a pure state. And in contrast, the other example, we have this weighted average, which really is a probability mixture. So we call this a mixed state. Okay. All right. Now, let's look at another example. Similar to the earlier one, so we're going to flip a coin. If it's heads, we prepare Kate plus. If it's tails, we prepare Kate minus. So I want you to figure out what the resulting states will look like in this density matrix form. So let me start the first step. So we know it's going to be a mixture of plus and minus. So what is this each individual outer product? Anybody? So again, what is plus? It's 1, 1. And row vector 1, 1. So this will give us this outer product. Okay, so if you just do the calculation, it's going to be all ones. And the outer product of ket minus will be something similar with additional signs. And if you add them, you can see this is half of identity. So did you notice something? This is the same as this one. Right? Flip a coin. And according to the outcome, you prepare either K0 or K1. That's one case. The other one, you prepare K plus or K minus. They give you the same density. And in fact, that means these two systems are identical. So density matrix is the full description of your system. You can have different ensembles that give you the same density. That's totally OK. All right, let's do another example real quick. Let me write down this matrix, P1, Pn on the diagonals, where these Pi's sum to 1, and each one is non-negative. OK, and everywhere else is 0. What does this density matrix correspond to? This is something we are familiar with. This is just a classical, not classical, this is a regular probability distribution. Right, each Pi is a probability, and they sum up to 1. So that means the density matrix representation subsumes classical distribution as a diagonal matrix. OK, and finally, one last example, which will be useful in some quantum crypto protocols. Suppose, let's say Alice samples some classical string x according to a classical distribution px, and then she prepares some other state, rho sub x, on another quantum register. OK, so there is a classical piece, which is the classical string x. Then there's a quantum register, which was prepared on a state rho, depending on the classical string. And how can we describe this whole system? Well, once I write it down, you will be convinced that this should be the right way to do it. So this joint system can be written as, first of all, the classical part, which is just outer product of x, this computational basis state. And for each x, since we prepare rho x, we write it on a separate quantum register. But then this is not done yet, because we sample x according to this probability distribution. We have to take this weighted average. So we have this scalar px in front of it. Okay, so this is what people call the CQ state, classical quantum state. Okay, so this is a very compact way to write down a system where there is a classical part and a quantum part. Okay, so there are some nice properties about density matrices which I'm not going to write down. For example, the trace, if you noticed, the trace of a density matrix is always going to be 1. And the density matrix is also positive semi-definite, meaning it has non-negative eigenvalues. Okay? And also a nice kind of condition is to test whether a state is pure is that the density matrix is pure if and only if you take the squared of the density matrix and it still has trace 1. Okay? It might be useful at some point. So this is the, yes? You're asking what I mean by classical distribution? Yeah, it's just, it's like I flip a coin, right? Then I get 0 with probability half, I get 1, or tails with probability half. So this can be a general probability distribution on a support of n elements, and you sample each element with probability p sub x. Okay? Or if you want to think of it in a quantum mechanical way, you sample x according to px, and then you encode your string x in this computational basis state kx. Then this will be the density matrix for that system. Does that answer your question? Yes. Cool. OK, so this is how we describe a quantum system or quantum state. Now we still want to apply operations. So let's first look at unitaries. And from there, we can generalize. Okay? So in our previous formalism, if you apply unitary on this psi, we will get U psi. Okay? Then how do you write down this resulting density matrix? So the input density will be psi, ket psi, bri psi. And then under this unitary, we can just write this state in this outer product form. And let's see what we get. So we have U psi and U psi dagger. And that will give us U psi and bri psi U dagger. And you can recognize this is exactly the input density. So this gives us U rho U dagger. So we are conjugating the input density by U. So on the left, you have U. On the right, you have U dagger. And this is true in general. Your input state here doesn't need to be pure. For any density, if you apply unitary, the resulting state will be U rho U dagger. Okay? Now, how about measurement? Well, it's kind of similar what you would expect. So suppose we measure this rho. So we're going to see some classical string X with probability this time will be determined by, conjugating rho with ket X. And after this measurement, the posterior state will be this density matrix, ket X, bra X. Okay, so at this point, you might be wondering, so far we're just reproducing everything in the previous formalism. So what's the point of introducing this new system? Well, the real power is we can actually, just now can talk about general quantum operations. So anything you can think of you want to do in your physics lab, we can describe them. So we're going to use this symbol. There's an input density rho, and then there's some operation, I call it capital phi, and then there's an output density rho primed. So this can be anything. Like it can be creating a qubit, creating multiple qubits, or throwing some of the qubits in your existing system, or any operation that's allowed by quantum physics. And formally, we call this a quantum channel. So let me give the mathematical definition of a quantum channel. And it's based on matrices. Okay, so let's consider M matrices such that if we take each one AJ dagger and multiply with AJ self and sum up all the J's, we get identity. So this is the condition we want for these matrices. And then from these matrices, we can define an operation. So rho will be mapped by conjugating rho with each AJ, and then sum over all the J. So this will be a quantum channel. It's a mapping from density matrices to density matrices. So let me highlight this mapping here. Okay, so you can immediately see the unitary case is a special case, because we know a unitary is satisfied, so there's only one matrix. And since it's unitary, U dagger U is identity, so it satisfies this normalization condition. And then the operation of applying a unitary is just conjugating the density by U. Okay? So that's not very interesting. So let's look at a more interesting example. And that's something you'll see and use a lot. So it's called partial trace. And the physical operation is pretty simple. Say you have two, like a composite system, say 2 qubits, and then you just discard one of them. And this is the partial trace operation. So again, said we have 2 qubits, X and Y. You just want to discard one of them. So how do you write this as a, mathematically as a quantum channel? So let me first draw this diagram here. So x and y. So this channel we're going to define is just to, discard the system y. Okay, so to describe this operation, we need to specify a bunch of matrices. So in this case, we need two matrices. Which is going to have this tensor product form. It's identity on X, which makes sense because we don't do anything on X. And then on Y, so this A0 matrix will have this bra 0 operating on the Y system. And the other one will be identity on X, but bra 1 on Y. Okay? So I claim these two matrices will define a quantum channel which exactly does this operation, discarding Y. And so I want you to verify that these two matrices satisfy this condition here. So it's valid, and let's see what it does. And I want to apply this to one of the EPR pairs. So do you still recall what the EPR looks like? Oh, I suppose so. So let's write it down. So I have half. Oh, it's going to be a little bit messy. We'll have 4 terms. Okay, now let's apply this operation to rho, which means we're going to conjugate rho by A0 and A1. So here's the rule. Okay, so it looks a little bit intimidating, but really, if you observe how we define A0 and A1, and then the form of this density rho, if you look at the second one, since we're conjugating by the same A0 or A1, it's only going to matter for the terms where, the Y system is in the same state. Because otherwise, you have bra 0 from left and bra 1 from the right. They will, since, 0 and 1 are orthogonal, so they will cancel. So what's left here will be just these two. And in fact, since we are, applying this bra to both sides, the second system will just give us a scalar. If it's 0, this one will kill this 0 and 0, and A1 will kill this 1 and 1. So we are left with half K0 bra 0 and half K1 bra 1. And this is just half identity. Okay? So keep this in mind. This will come handy when we get to quantum crypto, and this will be a useful identity to keep in mind. Okay. Suppose I need to speed up a little. All right, so finally, let's talk about general measurements. Okay, so the measurement we've been using so far is just measuring under the computational basis. And in general, merriment is just a special case of quantum channels. It can be defined by a bunch of matrices MA. And each A here will represent a possible merriment outcome. So we have a density, and we want to apply a merriment. So what happens is we'll see outcome A with probability, and then there's a posterior state. So now we just need to use the right linear algebra language. So the probability of seeing A will be the trace of conjugating rho by MA. And then the posterior state will be the same thing, but we have to renormalize it, so we just divide it by this trace, so that what's left is still a density matrix. So this is the rule defining a general merriment. Okay, so let's see why this makes sense by looking at a very familiar example, mirroring under the standard basis. So in this case, there are two possible outcomes, so we have to define two matrices, M0 and M1, and they're going to be very simple. K0 bar 0 and K1 bar 1. Okay, and you can verify using this new formalism, does this agree with the rule we talked about in the morning? Where we say, okay, you measure it, you're going to see 0 with probability proportional to your magnitude squared. You can, see if they match. And this merriment under the computational basis is a special case of an important family of merriments, which we call projective merriments. Right? Or it's also called von Neumann merriments. So in this case, each merriment operator, MA, is going to be a projection. So what is a projection? A projection is a matrix where the square is itself and the conjugate transpose is itself as well. So that defines a projective merriment. And finally, you will hear this a lot in the literature. And you'll see this term, POVM. Right? So this is another special family of merriments. And let me spell out the full name, which you don't have to remember it. Every time I have to look it up, what the full name really is. But you have to see it at least once, I guess. So it's called projective operator valued merriment, or just call it POVM. So what is POVM about? So in this merriment, our motivation is that we don't care about the posterior state. So we don't care about what's the resulting state after merriment. We just care about the statistics of this merriment. Okay? But as we can see, the statistics is entirely determined by this expression. That's the probability of seeing some outcome. And then there is a nice trick about trace. So let me write down. So we know we're going to see some outcome A with probability trace of MA, rho, MA dagger. But since trace is kind of cyclic, in the sense that you can move around this matrices inside, so we have trace of MA dagger, MA rho. So that means to determine the statistics, we don't need to know exactly what MA is, but just this MA dagger times MA. So we denote this as E sub A. So POVM, we just need to specify a bunch of matrices, and then we know we're going to see, when we measure under this POVM, we're going to see A with probability trace of E, A, rho. And again, we don't care about what the state is afterwards. OK, so let me pause for a second in case there are any questions or comments. Yeah. Oh, that's right. You're right. Did I say something else? OK. No. Thank you. Yeah. I guess that's why you don't have to remember the name. Just keep in mind that's POVM. Anything else? All right, cool. So this finishes this second system. We have density, we have general operators, which we call quantum channels, and merriments is a special case of quantum channels, and we have seen different families of merriments. Now, you might be wondering, this second system seems, a lot more general than what we described earlier in the morning. So when we restrict to state vectors and unitars and computational basis merriment, aren't we losing something? Okay, and the answer is no. These two systems are kind of equivalent in terms of expressiveness. Whatever you can describe in this system, you can simulate in the other system. And that's what we're going to do next. And I call this purification. I mean, clearly, this density matrix formalism subsumes the state vector formalism. But the more interesting direction is, can we simulate general operators or using just pure states, state vectors and unitary operators? So this is what we're going to address next. And just to look ahead, the answer is yes, and everything is going to be relying on a basic fact from linear algebra, which is Schmidt decomposition, which says if we have consider a system, a quantum state on two systems, and it's a pure state, let's call it psi AB. Okay, so Schmidt decomposition says there is a orthonormal basis for both system A and B. So I have IA, which is a orthonormal basis for system A, and another system IB. Sorry, another basis IB, such that this state psi can be written in a very nice form. It's summation over lambda I, IA, IB. These lambda i's are called the Schmidt coefficients, and they're non-negative and sum to 1. Sorry, they're square sum to 1. So this is Schmidt decomposition. It's just a fact from linear algebra, and it's true for any bipartite pure state. Okay. Now let's move on to the first kind of purification. Suppose we have a mixed state. Can we describe using a pure state, and in addition with some maybe a computational basis merriment? And the answer is yes. Right? So suppose we have a system A, which is in some state rho. It can be pure or mixed in general. And somehow we would love to cook up a pure state out of it. And the way we do it is to introduce a reference system R. And then there's a purification procedure such that the resulting state here, psi AR, is going to be pure. Right? And if we just ignore the reference system, we will recover rho, the original state on system A. So that means if you apply partial trace on the reference system R of this resulting purification, we get exactly rho. So just to be clear, this is a rho on the system A. Okay, so this means for any mixed state, you can use a pure state on on a bigger system, and then just ignore that reference system. We will still have the density on the original system. Okay. Do I want to show the proof? Yeah, maybe I can show you the rough idea. It's an application of Schmidt decomposition. Okay, so to start, since the density matrix is positive semi-definite, it has a spectral decomposition, meaning we can write this rho as under an eigenbasis with its eigenvalues pi. So this IA will be an orthonormal basis, and in fact, it's an eigenbasis, as I said. Okay? All right, so next we want to introduce a reference system such that, and define a pure state. What will be the natural choice here? So again, the goal is once we discard R, the reference system, we still have the original rho. Well, we just introduced a space of the same dimension and using the same basis. Okay, so we can define a state like this. Sum over I and IA, IR. But then what's important here is we want to make sure once we discard the reference system, we recover the original rho. So here, I'm going to write down pi square root here, because once you take the outer product, it gives us pi. And if we cancel the R system, we have the original density matrix. Okay, so you can verify once we trace out R, this is exactly rho. Okay, so from here, one observation is that the dimension of this reference system, it has to be at least as large of the dimension of the original system. Okay, and also when we cook up this pure state, it actually doesn't really matter what, let me put it in another way. Suppose I apply some arbitrary unitary on the reference system. Does that change anything on the reduced density on the A system? It doesn't. That means we have flexibility on how to purify the state. And this is an interesting property, which is, all the purifications, they're equivalent under some local unitary operation. Okay, so suppose we have two possible purifications, psi A1, AR1, and psi AR2. They are both purifications of rho A. Then we can apply a unitary on just the reference system. Let's say we apply on R2. Again, what's important is it's only acting on the reference system such that we can convert the second purification into the first purification. So they're equivalent under this local uniform transformation. Okay, and believe it or not, this is actually the fundamental reason that some lower bounds exist for information theoretical quantum crypto. And you'll hear more from a lecture by Anne Brabant. Okay, so this means we can purify a mixed state, meaning we can use a state vector to represent mixed states. How about general operations? And we can purify them as well. So more precisely, we can simulate general operators by unitaries. Okay, so suppose we have an arbitrary channel phi. It maps m qubits to n qubits. Then we can find a unitary acting on a larger system. Let's say m plus k qubits. And I'll explain what how large k needs to be in a moment. Okay, so this will still be the, maybe I can use a different color. This will be the original input system. Okay, and then we introduce this additional k qubits, which you can call reference, or physics call it the environment. I don't know how to spell it. Sorry, I think that's right. Anyways, so we can initialize in 0 state, and then the output here. On the top, let me change the color. On the top, that will be the n output qubits that I would love to have. And then there's just going to be m plus k minus n qubits, which we can just discard. So what it's saying is, for any quantum channel, we can cook up a unitary on a larger system, and it produces the same output as before for any input density. So this is called the Stinespring dilation, or just Stinespring form of a quantum channel. Okay, and as a special case, suppose we want to measure under a POVM. We can simulate the POVM measurement by applying a unitary operator on a bigger system and then measure under the computational basis. Okay, so this is how we simulate a general operator using just unitary and regular computational basis measurement. All right, let me pause for a second. And are there any questions?
What are the benefits of having a pure channel? You said convert to pure channel. Why does that help?
Right. So why is this interesting in any sense? Well, suppose we are still working with the quantum circuit model. We have quantum gates, which we can build arbitrary unitaries from them. So this means with just those finite set of universal gates, we can simulate any quantum channel, meaning any physical operation you might want to do in your physics lab. So everything we can simulate by a quantum circuit. A Schmidt decomposition of a Bell state. Well, I think, okay. Maybe we can work on it offline, okay? So, because that's I don't think it's complicated. Some algebra we can work on. Yeah. Any other questions? All right. Let's see. Okay, so I prepared some material on distances on quantum states and channels. These are useful when we want to talk about distinguishing two quantum systems, but maybe I'll skip it for now. And whoever needs this in the future can probably redo that. I do want to spend a little time to talk about something I mentioned in the very beginning. So this basically wraps up our introduction to quantum computing and quantum information. But as I said early in the morning, I want you to consciously think about the possible impacts of this new quantum information formalism on cryptography. So let's talk about it. Let's reflect what the impacts are, what changes could happen. So we've seen some unique features of quantum computing or quantum information. So there is superposition. And then we know quantum information cannot be cloned in general. And the merriment, generally speaking, they are destructive. And then there is also entanglement, which is a non-classical correlation. So all this, they contribute to these surprising quantum algorithms, right? And this quantum algorithm can sometimes solve hard problems, such as factoring and discrete log. And as a result, they break some of the popular public key crypto systems. So in response to this, we need to find out new problems which are hopefully hard for quantum computers to solve. And you'll hear some of these candidates in, I think, Craig and Chris' talk. Okay? But other attacks are also possible. So I guess from yesterday's lecture, you've seen in crypto many times there's an oracle involved, and we make queries to this oracle to try to figure out something. Okay? So what if the attacker gets superposition access to those oracles, such as a pseudo-random function or a random oracle? It turns out symmetric key crypto sometimes can be broken, and this includes some block ciphers, such as CBC MAC. Okay, as an application of Simon's algorithm. So that means this superposition here can bring out new attacks. And, oops. And in a paper in 2011, sorry, I missed an author. They showed that entanglement, can also be used to break some multi-prover or multi-sender commitment scheme. Okay, so entanglement can also be a source for attackers, a resource for attackers. Okay, and then we just mentioned this non-cloning feature, and this is problematic when the algorithm has some quantum side information. And there is also some construction of, extractors, which become insecure when the address has some quantum side information about the random source. Okay, so that means new attacks can appear everywhere. And really, here the bigger message is that we need to rethink how to model security when quantum addresses are present. And oftentimes, classical analysis, they would just fail. Such as, how do we copy and rewind a quantum address? And how do we fix the randomness of a randomized algorithm, of a quantum algorithm, for example, of the address? So here, the quantum random oracle model and zero knowledge are two representative topics. And you will hear more from two lectures, one from Dominic, the other one from Fermi. Okay? So that said, so far we've talked about what the attacker can take advantage of. But quantum information it cannot be just a troublemaker, right? Can we make something good out of it? Well, clearly, this non-cloning property is also alluding to something nice. Is there a scenario where you can think of where non-cloning can actually be a feature rather than a bug? Someone in the back? I'm sorry, can you speak louder? You can't distribute it. Exactly. And right, so one place we need this is what? Money, right? Banknotes. We would love to make sure nobody can counterfeit a banknote, or in general, copy protection. And in fact, this is what motivated the early ideas of quantum cryptography. So Wisner came up with the idea of quantum money, and then it inspired quantum key distribution. In recent years, there's lots of work on quantum copy protection, which essentially, is based on this non-cloning feature. So you'll hear more from Anne's talk. Okay. All right, that's one good thing that can come out from quantum information on cryptography. So I also want to mention for a long time, when we talk about quantum cryptography, the information theoretical security is kind of the golden standard. But in recent years, relatively recent, it becomes evident that quantum information plus some computational assumption, this is equally exciting. For example, you can reduce some of the assumptions that you would need in classical cryptography. And one notable example is what you'll hear from Dakshita's talk, where one-way functions plus quantum information, we can construct quantum multi-party computation particles. And this is believed unlikely by using classical crypto alone. Okay? And I think everybody should appreciate that one-way function is considered the bare minimum assumption in classical cryptography. But in fact, one-way function might not be the minimum assumption needed in this case. So there is another quantum computational primitive which was introduced in one of my work with my co-authors in 2018, I think. Yes, yeah. Which is called pseudo-random quantum states. So again, it's a unique quantum cryptographic primitive. It doesn't seem to exist unconditionally, so it's still a computational assumption, but it seems to be weaker than one-way functions. So you can build this from one-way function, but it doesn't seem to imply one-way functions. And it turns out, in some recent work, this pseudo-random states, quantum states, can be used to build quantum MPC as well. So one-way function might not be necessary. Okay, so this is another interesting direction, and again, you'll hear more from Dakshita's talk. Okay, and let me just mention one final thing. So usually when we think about quantum algorithm in the context of cryptography, we think of those as something an attacker would use, would take advantage of. But can quantum algorithm help us as a designer of some sort? One possible place is using quantum algorithm in cryptographic reductions. Meaning, suppose I want to build, I don't know, a pseudorandom function. Do I want that? Let's say I want to build a one-way function based on some NP-hard problems. And we know classically, so what does this mean? This means I start from an NP-hard problem, I build a candidate function. I want to prove this is one way, meaning any attacker that can invert this one function, I can use it to solve I want to use it to solve my NP-hard problem. And this is a reduction. And classically, if you only have a classical reduction, there's strong negative evidence saying, no, you cannot do it. But what if we can use quantum algorithms to build this reduction? Would that help us to build one-way function based on NP hardness? Okay, this is a possible direction that quantum algorithm can actually do some good for cryptographic designers. So far, there's little work. I did something on this, but it's still negative evidence, not as strong as the classical one, but I think there's still room. So let me just write down quantum reductions, such as building one-way function from NP hardness, from NP complete problems.
Is that from worst case hardness?
Uh-huh.
Worst case?
Yes, let's say worst case. Let's shoot for the ideal case. Okay, so this is the kind of the picture I want to show you in the end, which also alludes to the future lectures and something for everybody to think about. What are the possibilities and maybe interesting open questions there. And with that said, I'll stop here, and I'm happy to take any questions.